In this video, we're going to recreate the classic arcade game Asteroids from scratch using JavaFX. All right, so first, we're going to start off, we've got a new project. We start off with a class called Asteroids, and we're going to extend the application class from JavaFX. All right, for our public static void main, string bracket args, we're going to do a try to launch the application with the arguments. As always, we need to catch exceptions. In case of an exception, we'll go ahead and do a print stack trace. And finally, we'll just do a system exit. All right, because we're extending the application class in JavaFX, that means we need to create a public static void start method. So public void start, and this is going to take in a stage. We'll call that main stage. In the main stage class, let's see, we could start off by setting the title for the stage. So main stage.set title to Asteroids. That is the name of the game. And the very last line of code we'll want to do is main stage.show. And already we do have an application we can run. It'll be pretty boring at this point, but if we give that a run, we should see a nice blank screen. There we go. There's our blank application. All right, so let's add some content here. I'm going to use, for a layout manager, I'm going to use a border pane object. I'll call that root. It'll be a new border pane. And then I'll create a scene built on the border pane. Call this scene main scene. Should import the scene class. Main scene is equal to a new scene with root. Then I'd like to, let's see, I want to attach the scene to the stage. So main stage.set scene to be the main scene. Then to display my graphics on for this game, I'm going to go ahead and create a canvas object. And I'm choosing the JavaFX canvas class. Call that canvas, that'll be a new canvas. Let's make that 800 by 600 pixels. In order to perform draw operations on the canvas, I'll need to create a graphics context object. Graphics context. I'll just call that context for short. We get our context object from the canvas. Then I need to actually add the canvas to the root. And the border pane allows us to set containers, to set objects and nodes in different regions of the screen. I'd like this canvas to be directly in the center. And just to illustrate how this works, maybe we'll just draw a nice large blue rectangle in the center of the canvas. So context, I'll set the fill color to be the color dot blue. It's one of the predefined colors. And I'll say context dot fill a rectangle from 0, 0 to 800, 600. That will fill up the entire canvas. All right, I'd like to go ahead and run this. And here we go. We have now a large blue screen. All right, so before we get going with adding a lot more functionality here, we're going to need to add some helper classes to provide the basic functionality common to all games. In particular, we're going to create 3 classes. One such class is going to be called the vector class that will store pairs of numbers and perform operations. We'll have a rectangle class, which we'll use for basic collision detection. And then we'll have a sprite class, which will manage all our in-game entities. So I need to add a few new classes. The first new class I'd like to add will be the vector class. All right, so this isn't particular to JavaFX. Let's go ahead and start off with a constructor. And what information is a vector class going to store? Perhaps it'll store a double called x and a double called y. All right, the default constructor will set both of these values to 0, but in the interest of reducing a lot of future code, let's write a set method right away, which takes in a double x and a double y, and sets this dot x to x and this dot y to y. Then in the default constructor, we can just say this dot set 0, 0. Right, creating a vector with no arguments, we'll set it to be the 0 vector. Let's also create a parameterized constructor, a public vector, which takes in double x, double y, and we'll set the values to x and y. Okay, next I'd like to go ahead and perform some operations on vectors. There's a few which come to mind. First, let's say public void add. Wanted to add in two values to x and y. And I'll call those dx and dy. And we'll just add them to the x and y components, respectively. So this dot x plus equals dx, and this dot y plus equals dy. Let's also say public void, sometimes we'll want to multiply a vector by a constant. So maybe we'll call that constant m. In this case, this dot x times equals m, and this dot y times equals m. This will be good for scaling our vector, for stretching it or shrinking it. So we have an add and a multiply. Next, we'd like to get the length of a vector. So this will return a double, and we'll call this getLength. And we'll return, see, we calculate the length using the Pythagorean theorem. It's the square root of the x component squared plus the y component squared. Right, and that's how we calculate the length of a vector. Next, we might want to set the vector to have a particular length. So public, this will be void, there's no return here. Set length to be some new length L. All right, in order to set the length, I'll do this in two steps. The first, we have to take into account that the vector might already have a length which is not equal to L. So first, I'm going to use the multiply function to change the length of the vector to length 1 by dividing out by its current length. And then I'll scale it so it has length L. So step 1 is find the current length of the vector. So we'll create a double, call that current length, is equal to this vector, get its length. And then if the current length is 0, right, then we have a little bit of a problem, right? If we try to multiply the components of the 0 vector by something, that's not going to work very well. So let's add an if statement to protect against that. So this will be to guard against division by 0 later. If the current length is equal to 0, then we'll just return right away We'll assume we can't change the length of a zero vector. If we multiply it by anything, it stays the zero vector. Else, what we'd like to do, let's see, we want to divide this vector. Right? So instead of else, let's just do this. Let's say this dot multiply by 1 divided by the current length. Right? And the purpose of this step is to scale vector to have length 1. And so this divides out by its current length. Then we'll do one more step, scale vector to have length L by saying this dot multiply by L. All right, so first we scale it down by dividing out by the current length. Then we scale it up by multiplying by L. Excellent, so we can now get the length and set the length of a vector. The other two important pieces of information are the angle at which the vector is pointing. Right, so we'd like to write a similar pair of methods. First, public double get length. Sorry, not get length, get angle. And we will also want a public void set angle. And this, I like to work in degrees. So I'll say this takes as an input double angle degrees. So we'd like to write these two methods next. Understanding how to write these methods from scratch involves a little bit of trigonometry. And for that purpose, I have a diagram ready to show you. So here, we're going to have a vector represented by this arrow from the origin to the point xy. And let's say it has some length L. What we want to do is set the angle that this vector makes with the x-axis, which is indicated by the Greek letter theta. And the way we'll do this, from our vector, we'll drop down a perpendicular to the x-axis, so we have ourselves a right triangle. And from, with respect to this angle theta, the opposite side of the triangle has length y, and the adjacent side has length x. Now from trigonometry, we know that the sine and cosine and tangent functions are equal to ratios of the different sides. So for example, tangent of theta, tangent of the angle, is equal to the length of the opposite side divided by the length of the adjacent side, so that's y over x. So tangent theta is y over x, which means we can calculate theta by calculating the inverse tangent, or atan, of y over x. Now, unfortunately, there might be some unwanted cancellation of signs here. Right? The atan function can't tell the difference between if y and x are both positive or both negative, and the negatives cancel out. So we actually need to use a different function called atan2, which is like arctangent, except it takes in the numerator and denominator as separate arguments, so it doesn't lose any negative signs that could be canceled out. So we'll use this fact to figure out what the current angle is. So heading back to our project, to get the angle, what we need to do is return math.atan2, and we're going to say this dot y, comma this dot x. A little bit of trigonometry tells us what we need. Now, in order to set the angle, right, if we're given an angle in degrees, again, let's go back to our picture for a moment. Right, let's say we know what we want the angle to be. The vector already has a fixed length L. We want to change it to have some angle theta. Since we're setting the angle, we need to find the new values of x and y. But those can be calculated using our other two trig functions, sine and cosine. And so the sine of the angle times the length will give us the y component, and the cosine of the angle times the length will give us the x component. Right, so we need to calculate the length, and then we'll perform this calculation. Right, so heading back to code again. First, we'll go ahead and calculate the length. So double L is equal to this dot get length. And then since the math, sine, and cosine functions expect angles to be in radians, let's also create a double angle radians to be math dot, we're going to convert to radians, what the angle in degrees is. Then we'll figure out the sine and cosine and use that to set x and y. So this dot x, as we saw before, is going to be the length times math dot cosine of the angle in radians. Similarly, this dot y will be equal to L times math dot sine of the angle, again, in radians. All right, with that function, our vector class is complete. That's all the functionality that we're going to need. But actually, one thing I should say in terms of consistency, set angle takes an angle in degrees. To be consistent, I'd also like get angle to return an angle in degrees. So let me say math.2 degrees of math.atan2. Again, the math class trig functions by default turn things in radian measure, but will return a degrees value. All right, so that's the vector class. That sounds great. Next, we're going to create a class for collision detection. So I'm going to create another new class. This class will be called rectangle. All right, the data we need for a rectangle includes the top left corner, which will represent as a point, xy. So xy represents the top left corner of the rectangle. So we'll store a double x and a double y. We also need to store its width and height. All right, so first we'll create a few constructors and a few set functions. And so first, let's say public rectangle. This will be the default constructor. But before I write it, I'd like to write a couple of set functions. So maybe I'll start with public void set position, double x, double y. And this function will say this dot x equals x and this dot y equals y. Let's also do a set size function, public void set size, which will take in a double for the width and a double for the height. So this dot width equals w and this dot height equals h. All right, so for the default constructor for the rectangle class, let's say this dot set position to be 0, 0, and this dot set size to be 1, 1. So a very small rectangle. Let's also do a parameterized constructor. So public rectangle, let's see, double x, double y, double width, and double height. So again, we'll use the set functions. We'll say set position with the x and y, and set size using w and h. All right, so these are the basics of the rectangle class. Now, the main method which we need for rectangles, we need a way to detect if two rectangles overlap. And so we're going to create a public Boolean function called overlaps to check if this rectangle overlaps with a rectangle called other. But once again, before we actually write down the expression which checks if two rectangles overlap, it'll be good to take a look at a picture. So let's open up a picture. All right, so here we have two rectangles. We have a rectangle on the left, think of that as this rectangle, and a rectangle on the right, the other rectangle. And before we talk about two rectangles overlapping, let's instead talk about the opposite situation. How can we tell if two rectangles do not overlap? Well, there's something called a separating axis, represented by this dashed line in between them. If two rectangles do not overlap, we must be able to draw an axis or a line which separates them. There's really 4 different cases, which are all shown here below. In case number 1, the red rectangle is completely to the left of the blue. Case number 2, red is to the right of blue. In case 3, red is below the blue. In case 4, red is above the blue. So we can check for each one of these cases by comparing the coordinates of 2 of the edges. For example, in case 1, we can tell that the left rectangle, the red rectangle, is to the left of the blue rectangle because the right edge of this rectangle is less than the left edge of the blue rectangle. In other words, this rectangle's x plus w is less than the other rectangle's x. Right? And each one of those 4 cases can be written as a comparison. So let's go back to code. Right, so first we're going to create a Boolean called no overlap. Right, and to calculate if there's no overlap, again, there's a few different cases we want to consider. Right, so there's no overlap if this rectangle's x plus width is less than the other rectangle's x. Right, that's the case where the first rectangle, right, so this is to the left of other. The next case we'll want to check to see if there's no overlap is this is to the right of the other, or equivalently, the other dot x plus other dot width is to the left of this. Right, that's going to be the next case. Let's see if I can line these up. All right, let's try that. And then the next case, right, this next case was this was to the right of the other rectangle. The next case, if this rectangle, right, let's take a look at the bottom edge. So this dot y plus this dot height is less than the other's y coordinate. Right, that refers to when the bottom edge of this rectangle is above the top edge of the other. So that refers to the situation, this is above other. And finally, the other one is the opposite of this. Other dot y plus other dot height is less than this dot y. And so that's the 4th case, when the other rectangle is above this. Right, so a total of 4 cases where there is no overlap. Right, and it's possible for more than one of these cases to be true. Right, it might be the case that you're both above and completely to the right of the other rectangle. But at least one of these must be true if there is no overlap. That's the separating axis theorem. However, since we're interested in returning whether the 2 rectangles do overlap, our return value here will be not no overlap. And so it's like a double negative. The not no overlap means it'll return whether or not the 2 rectangles truly do overlap. All right, so that's it for the rectangle class. Again, we're going to mostly use it for collision detection. Next, we're going to create another class. This class is going to be our sprite class. A sprite is some kind of on-screen entity which can move around the screen. And sprites, they store a lot of data. Let's see, they'll store a position, which we'll store using our new vector class. And let's say also a public vector to store some type of velocity. We'll use a double to store some amount of rotation. And again, we'll think of that in degrees. We also have a boundary for each sprite to determine when one collides with another. So we'll store that using our rectangle class. And finally, each sprite is represented with some kind of an image. So I have a public image, just called image. Okay, so let's go ahead and create a constructor, public sprite. The default constructor, right, will just initialize most of these objects. Position equals a new vector. Velocity is equal to a new vector. I do like to say this dot. What else do we have to initialize? The initial rotation will be 0. The boundary will just be an empty rectangle. This will be a new rectangle. And the image, I'm not sure what the image is going to be yet. Maybe let's create a set image class, or sorry, a set image method, public void set image, which takes in an image, or not an image, let's say it will load the image for us. Let's make life easier on our future selves. String will take in some file name. Let's say image file name. Right, and what we'll do here, we'll go ahead and load this image. Right, this image will be a new image object. We need to pass in the image file name. And while we're at it, once we've loaded the image, we now know what the width and the height of the boundary rectangle should be. So let's also say this dot boundary, we can now set its size according to this dot image get width and this dot image dot get height. So when we set the image, we'll also set that. Now it might be the case that when we initialize the sprite, we might want to pass it an image right away. That's certainly possible. So let's set up a parameterized constructor as well. Let's say public sprite, which takes in as a string an image file name. And then in this method, this constructor, first we'll run the default constructor, and then we'll run the set image, just say set image, using the image file name. So it'll call that method for us. Excellent. Now, what else do sprites need to be able to do? Well, we've set the size of the boundary rectangle, but we also need to possibly constantly update the position of the rectangle as well. If our sprite is moving around the screen, if the position gets updated, then we'll also want to change the boundary as well. So what we'll do, the way I usually like to handle this, is by only accessing the boundary with a method called getBoundary. And what this method will do, it'll also take, before it returns the boundary object, this dot boundary, it'll update the position using this dot position x and this dot position y. And then it will return this dot boundary. And so it updates the boundary just in case and then returns it. All right, we're going to be very interested in whether or not two sprites overlap. So let's create a public Boolean overlaps. And this will check it against a sprite called other. You might recall that we had an overlaps method for the rectangles. And sure enough, the overlap method on the sprites is basically going to call this getBoundary method and then delegate to the overlaps method in the rectangle classes. So we can actually do this in one line. Let's say return this dot getBoundary and check if this boundary overlaps the other object's boundary. So this will check if two sprites overlap. Excellent. We also want to write an update method, public Boolean update. And in particular, one piece of information which is often useful when you're writing an update method is to keep track of how much time has passed, which is sometimes called delta time. Usually, if our game is running at 60 frames per second, delta time will be 1/60th of a second. Right now, the only thing we actually have to update, if there's a velocity that's been set, we might want to use that to update the position. So let's say this dot, or let me put in a comment first. Update the position according to velocity. So this dot position, we're going to add to this position based on what the current velocity is, and also taking into account how much time has elapsed, that is delta time. So we'll say this dot velocity dot x times delta time, and this dot velocity dot y times delta time. Right, there might be other things that need to be updated as well. In theory, for a more complicated game, you might see yourself extending the sprite class and overriding the update method. There's lots of things you could do with this. The last thing we need to do is actually render this sprite to this screen. And we'll have the sprite kind of take control of that operation by itself as well. Let's call this public void render. And it draws the sprite on the screen. In order to draw an object onto a canvas in JavaFX, we use the graphics context object. So I'm going to take in a graphics context called context. Let's see. In order to render something to this screen, right, the image, I want to do two things. I want to put it at the correct XY position. I also want to rotate it according to the number which is stored in this dot rotation. So I'm going to go ahead and write out some code, and then I'm going to explain what it does. So I'm going to save the context. Let's see, I'm going to want to translate it according to this dot position dot x, this dot position dot y. I also need to take into account rotating. Let's take something in degrees, which is how we're storing rotation. This is probably going to look a little bit strange. This dot image dot get width over 2, and this dot image dot get height over 2. Then context, I'm actually going to draw the image. So this dot image with no more translation, and then context dot restore. All right. So some of these might make sense if we're trying to draw something on the screen. We have a call to draw image, and there's going to be some translation according to the position, and also some rotation according to the rotation. But then there's also this weird translate, which takes half the width and half the height. The reason for this line of code, this particular context.translate, is when you rotate something in computer graphics, by default, rotation takes place around the origin. In this case, that would be the top left corner of the screen. Right, but in this case, we don't want to rotate around the top left corner of the screen. Normally, when we're rotating a sprite, rotation naturally happens around the center of that sprite. So what's happening here? We first take the image, and we're going to draw it with its top left corner at 0, 0, and then we're going to translate it. Actually, I want to make both of these negative. It's going to be very important, making them both negative. This will slide the image so that its center point, which is half the width and half the height, we're going to slide it to the left and up. So the image, after this line of code, is now centered at the origin. Now we do a rotation around the origin, but that rotation around the origin is also aligned with the image's center. So it rotates in the direction we want it to be rotated in. And then we're going to translate according to the values stored in position.x and position.y. Right, and it's very important to know that since we previously translated it so the object, the sprite, is centered at the origin, we're translating the center of the object to position.x and position.y. So in the future, when we set the position of a sprite, we have to remember that we're really setting the position of its center. All right, excellent. We now have a render method. Well, I should also say that save and restore. Save and restore allow us to apply these transformations to only this particular sprite. Restore kind of erases all these changes, which will be important when we're rendering the next sprite. And we should also take note that you can think of these graphics operations as kind of happening from last to first. Right? So as we were explaining it, we draw the image, translate it, then rotate it, then translate it again. All right, I think that's enough for the sprite class for now. We're going to head back to the Asteroids class, and I'd actually like to start creating some sprites and start drawing them on the screen. So what I'd like to do now is actually want to take, I have a folder of images here. Right? This contains a laser and a rock and a space background, and I don't know why this is called spaceship.copy. I'm going to go ahead and change that to just spaceship.png. Right, so I have this class right here. Let me go ahead and close some of those windows. I'm going to take this images directory and I'm going to copy that into my project. And so right in the source folder, I like to copy those 4 images. Right, so for instance, I have a laser that I'm going to shoot later on, have some rocks, have a spaceship, and have a picture of outer space. Right, those will all be handy later on. Right, back to the main class, the Asteroids class. Right, instead of just drawing a blue background here, let's go ahead and create a sprite. Sprite, we'll name that background. Let's make that a new sprite. And let's use the parameterized constructor where we go into the images directory. And then what I'd like to do, I remember I need to set the position of each one. Background.position.set. And I'm setting the coordinates of the center of this object. Since my canvas is 800 by 600 and I want this to be centered on the screen, I'll set it to be 400, 300 for its position. And then I'll ask the background to render itself to the screen using the context attached to this canvas in our JavaFX application. Whew. All right, there's a lot going on here. Let's go ahead and give this a run. Hopefully we'll see an outer space background. Oh, I'm missing a return statement. Let's see, I have a public Boolean update. Oh no, that's going to be a public void update. That's strange. I wonder why I tried to do that. Let's go ahead and try running this again. Running the Asteroids main function. Oh, it looks like I have something else I've got to look at. Let's see, I need to be able to find that image file. Let's see, in my project source, I have images and space.png. Let me think about this for a second. All right, so after refreshing the directory, making sure the directory is placed correctly, and going back up to run the class's main method, I should be fine now. Yep, there we go. So I have my outer space background. Now let's add some more things. Right, next, I'd like to perhaps add a spaceship. And so again, going back down to the start method in the Asteroids class, let's create a sprite called spaceship. This will be a new sprite. using the image from the images folder spaceship.png. This one, I'll set the spaceship position. Let's set that a little bit further to the left, so maybe 100, 300 as its center point. And then we'll ask this spaceship to render itself using the context object. All right, let's go ahead and run this again. And sure enough, there's our spaceship sitting to the left in our outer space. Now, the next thing I'd like to do is I'd actually like to make this spaceship move. So I'm going to set up something called an animation timer. It's a way you can create a set of code that will run 60 times per second in JavaFX. So I'm going to create an animation timer. I'll call this the game loop. It's going to contain all our repeating game loop style code. This will be a new animation timer object. And when you create an animation timer, it's like you're implementing an interface, kind of like an anonymous inner class. And we need to write a method with a signature public void handle, which has a single parameter, a long called nanotime. And here we can write the code that we want to run. I'll probably never use nanotime, to be honest. But let me take the spaceship. Let's give it a default velocity. Say spaceship.velocity.set to, let's just have it move slowly to the right. So at 50 pixels per second. All right, I also want to take my render statements. I'd like to move those into the game loops handle function. And so background render and spaceship render, let's put those down here. Very good. And also we need to update the position of the spaceship. So let's also run spaceship.update. We have to say how much time has passed. In JavaFX, the animation timer runs at 60 times per second. So every time a handle is called, 1/60th of a second has passed. Okay, now let's go ahead and run this again. Right, if everything goes according to plan, we should see the spaceship slowly moving across the screen, going to the right. Where is that spaceship? So we have the spaceship position, spaceship velocity. Oh, you know what we forgot to do? We set up the game loop, but we never actually started the game loop. Huh, that was very mysterious. So one more line of code we need to add, and then we'll run it again. Game loop dot start. There we go. Now, hopefully we'll see a spaceship running across the screen, or flying rather. Excellent. That looks great. Okay, the next thing I'd like to do, I'd like to get some user control over this spaceship to help the spaceship move around the screen. To do that, I'm going to need to use something called an event listener. An event listener is something which responds to some kind of user-driven action, like a key press or a mouse press or something like that. So I'm going to set up, not only that, I'd also like to set up an array list, which will contain the names of keys that we're currently pressing. So I'll do the array list first. I'm going to go ahead and create a string. First, I should go ahead and import array list. An array list containing strings. I'll call this pressed key list, key pressed list, key pressed list. That'll be in a new array list containing strings, the names of keys. And I'm going to set up an event listener now. This will attach to the main scene. We want to set some code to run on, there's lots of events you can respond to, as you can see by autocomplete. I'm really interested in set on key pressed. All right, now to specify the code that's going to run, I need an event handler, which I could write with an anonymous inner class, but I'd really like to use a lambda expression here. I'm going to create a key event. And the code that will run, let's see, on the key pressed list, I want to get the name of the key that was pressed and then add it to the key pressed list. So let's say for this particular event, first I'll create a string called key name. And this will be from the event, get the code for the key and then convert that to a string. And then I also need to avoid duplicates here. Oh, I also need to import key event. Okay, if the key pressed list doesn't already contain the key name, then we'll add the key name to it. So the purpose of this if statement that I'm writing is to avoid adding duplicate names to the list. Avoid adding duplicates to list. So if this key name is not already in the list, in other words, if not key pressed list dot contains the key name, then we'll say go ahead and add that name to the list. Key pressed list dot add key name. All right. Right, so now whenever this window has focus and we press a key, this lambda expression will be executed and the name of the key will be added to this list. Similarly, I'd like the same event, but for when a key is released, I'd like to remove the name of the key from the key pressed list. So I'm actually going to start by copy pasting this block of code and change this from on key pressed to on key released. And so here, let's see, first get the key name. And then I'll say if the key pressed list does contain the key name, then I would like to remove it from the list. I'm pretty sure it'll always contain the key name, and even if it didn't, this line of code wouldn't actually do anything, but I like the nice parallel structure here. All right, so this will store a list of keys which were pressed, and now let's go back to our game loop. Let's actually set up something where we process some input. Right, let's check to see if certain keys are pressed, maybe the left and right arrow key, and we'll use that to spin around the spaceship. So here, let's say in our animation game loop, in our handle function, let's go ahead and process user input. Right, so let's say if the key pressed list contains the key called left, that's if you're holding down the left arrow key. In that case, we'll say spaceship dot rotation minus equals 3. So in this case, 3, that's 3 degrees. And remember, the game loop runs at 60 frames a second. It executes the handle method 60 times per second. So really, this rotation speed, it looks small, but 3 times 60 is 180. So this would be rotating 180 degrees per second. Similarly, let's say if the key pressed list contains right, then we'll go ahead and add 3 degrees to the rotation. Right, so still we have a velocity that's set, so the spaceship will continue moving to the left, but now we should be able to make it spin in either direction. All right, let's go ahead and run this again. I'm pressing left, spins to the left, and pressing right, it spins to the right. Whee! Okay, next thing I'd like to do, I'd like to have control over forward motion. Right, no more of this spaceship velocity set, no more of this automatic movement. We're going to take control. Let's say maybe if the user presses the up arrow key, we'll set the spaceship velocity. Right, but we need to do this in a clever way. Right, pressing up doesn't necessarily move the spaceship up. pressing up moves this spaceship in the direction that it's currently facing. And this is one of the reasons we spent so much time writing the set angle and get angle methods. And so if key pressed list contains up, and then I want to do a couple of things. First, spaceship dot velocity dot set length. I think this is kind of the speed. The length of the velocity vector is the speed it should be traveling at. So maybe I'll set that to be 50. It's important to set the length first, because setting the angle of something which has no speed doesn't really have a well-defined meaning. Next, I'll say spaceship.velocity.setAngle to be whatever the spaceship's current angle is. And so it'll be spaceship.rotation. Right, so if the spaceship, if we press up, then that will be the current velocity. Otherwise, right, so we're not pressing up. Otherwise, let's say maybe spaceship dot velocity dot set length to be 0. And that, in effect, will stop it from moving. So this isn't 100% true to the original Asteroids game. In the original Asteroids, you would accelerate and decelerate, and once you let go of the arrow keys, then you would just continue floating in whatever direction you were moving in before. So it's a little bit simpler because we're making this from scratch in JavaFX, but still, this should work pretty well. Let's go ahead and give this a run. And so I can push, let's see, if I push left and right, pushing up doesn't seem to be doing anything. Let's go back and look at that code quickly. Right, so if the key pressed list contains up, then we should set its velocity, the length of its velocity to 50, and then set the angle at which it's moving, like so. I'm a little bit surprised. I expected this to work. Let's think about this for a moment. If this isn't working, there must be something wrong with set length. So let's go over to the vector class. And here's our set length method. Oh, do you know what? Okay, I think I know what it was. Initially, the velocity vector is the 0 vector, right? So we don't actually want to return in this case, right? We do need to be able to set the length. The only problem with is this wasn't very well defined. So if current, let's say if current length is 0, then current angle is undefined. So we'll have to make an assumption. We'll assume the current angle is 0. And so pointing to the right. So in this case, what we'll do is say if the current length is 0, let's instead do something else. Let's say this dot x, or let's make this even simpler. Let's say this dot set. Now I do need to put this in a block. This dot set L0 and then return. Or, it'd be nicer. Let's actually use the else here. This way I don't need a kind of misplaced return there. All right, so if the current length is 0, we'll just say the vector will point to the right by default. Otherwise, we can use scaling, dividing by the current length, then multiplying by L to preserve the angle. So else we're able to preserve current angle. All right. That sounds good. Let's go back to the Asteroids class. Let's go ahead and run this again. There we go. I can press up to move forwards. I can turn and move all around. Very good. I might also want to increase the speed at which the ship moves. Perhaps instead of setting this to 50, maybe I'll set this to 150. Get my spaceship moving a little bit quicker. Cool. All right. The next thing I'd like to do is avoid something like that. Where did my spaceship go? I have no idea. In the original Asteroids game, that featured something called wrap, meaning when a ship went off, or any object went off one side of the screen, it reappeared on the other side of the screen. So I'm going to go ahead and head back to the sprite class. I'd like to add a new method to the sprite class to make this a little bit simpler. And so in update, let's see. Maybe I'll write the method wrap, public void wrap. So wrapping is optional. Right, in the wrap method, what we want to do is check if the object has gone completely off the screen. So for example, if we go off screen to the left, right, so if this dot x plus this dot width is less than 0, that means the right edge has gone all the way past the screen, and it should reappear on the other side of the screen, which means the wrap method will need to know what the width of the screen is. So we'll have to pass these in as parameters. And so if we go off one side of the screen, we'll reappear. We'll set the x coordinate to be the width of the screen in the other direction. Similarly, let's say if you go off the right side of the screen, right, if the x coordinate goes past screen width, then we'll set this dot x to be equal to, let's see, it's kind of the opposite of the first if statement. We want this dot x to be negative this dot width. And so this places it so it's aligned with the left edge of the screen if it goes off the screen to the right. Similarly, if this dot y plus this dot height is less than 0, it occurs to me that actually we don't have this dot x and this dot y. I'll finish writing this code, then I'll actually define what these are. All right, let's see. Then this dot y should equal the screen height. Yes, that means we've gone off in this if condition. We've gone off the bottom edge. Right, so now this is if we've gone off the top edge, right? The bottom edge is less than 0. So the bottom edge of the sprite is less than the top edge of the screen. This dot y is equal to screen height. Right, this will pop it back down on the bottom. And then similarly, moving past the bottom edge of the screen, we determine by this dot y being greater than the screen height, means we should set this dot y equal to negative this dot height. All right, so I was kind of thinking in pseudocode here. X and width and Y and height aren't really fields in a sprite. X and Y are stored in the position. So what I'll just do to make the code a little bit more readable, let's say double X equals, I don't want to do that. I could just insert this dot position dot X. I'll just insert a position dot for each one of these. Similarly, I don't have width and height. What I could do is this dot get image dot get width. Wait, this dot get image, that's not a thing. This dot image dot get width. Every time I see that this dot width, I'll replace it with this dot image dot get width. This dot height, I'll replace with this dot image dot get height. And I'll do the same thing down here. All right, that looks pretty good. Right, that's the code which will allow a sprite to wrap around the screen. If it goes past any one of the 4 edges of the screen, it should reappear on the other edge. Now in the update function, in the Asteroids game, all objects wrap around the screen. And so in update, I'll say wrap around screen. So comment for the next line, this dot wrap, our screen is 800 by 600 pixels. All right, in this case, with this addition to the update function, hopefully we won't lose our spaceship. So let's go back to the Asteroids class. Let's run this again. And here it comes. There's our spaceship. Let's go off the screen and we reappear on the other side. Go off the bottom, we'll reappear down there. Go down here. All right, that's looking about as good as we're gonna get it. Right, one thing which might look a little bit strange, sometimes it might look like the spaceship is disappearing a little bit prematurely. Right? Part of the reason for this is, remember, X and Y are actually measuring the center coordinate of the spaceship. So really, I should take that into account as well when we're doing the wrap function. I'll turn that into a to-do for now. Take into account the center of the object. Let's see, unless there's a really easy way to do this, let's think. If I just divide the get width and the get heights by 2, let's try that real quick. That's often the kind of change we need to make. So let's see. With that change, if we rerun the code, does that work? If so, great. If not, we'll leave it on the to-do list. I'm not 100% convinced that's much better. Right, it seems when I get close to the end, right, it pops back on halfway. Oh, it's because we need to make a similar change over here. Right, this dot position dot x is equal to screen width. Right, but we also need to take into account half the width as well. So the x position isn't just the screen width, but the screen width plus. And we're taking into account this dot image dot get width over 2. All right. Let's try this, see if this looks better on moving to the left and to the right. And if so, we'll apply the same change to the screen height as well. So let's go ahead and run. Let's try flying off the left side and the right side of the screen. Going off the left. Oh, that looks much better. Yep, that's pretty much perfect. Cool. All right, this code is just getting really kind of a mess to read. Let's say double half width equals this dot image dot get width over 2. Let's add this in at every place. It makes the code a little bit shorter. Let's see, and then we want to do the same thing for the height. Double half height is equal to this dot image dot get height over 2. And half height we'll use here. I'll make this screen height plus half height. Screen height plus half height. And minus half height. All right, we've now taken into account the center of the object. The wrap function looks pretty good. We've been going at this for a while now, so maybe we'll take a break here and we'll continue the Asteroids game in the next video. Thanks for listening.